Well, thank you for joining us today. I'm Mike Dimick from Caterpillar, and I'm so excited to be hosting today's webinar. Really, anytime you say you are working with NASA, it's pretty cool. And the Centennial Challenges give anybody the chance to be part of a NASA mission, and that's why we're here today. We hope you decide to get involved in the 3D Printed Habitat Challenge. This is an opportunity to be part of something truly important, but it's definitely something that is not going to be an easy challenge. We know that the challenge is going to be a lot of work. So as you're forming your teams and deciding on how to get started, we have pulled together a lot of the experts that you see in front of you today to walk you through the contest and answer your questions. I know these are people you're going to want to hear from, so let's get started. I'm going to turn it over to Monse Roman from NASA. Monse?
Well, good afternoon, everybody. It is our pleasure to be here today. On behalf of the NASA Centennial Challenges Program Office and NASA agency-wide, we're excited to have the opportunity to let you know what we're doing and hopefully invite you to come and participate in our journey to Mars. This is the way that we as an agency reach out to all of you, our nation, to come and help us put a little piece of our puzzle in the journey to Mars. It is a very hard job, and we need minds from basically all over the world to come and fill out those little pieces that we're still missing. And hopefully this challenge will help us do that. This challenge, as you probably already know, it's about what a house on Mars will look like. And this is a very simplistic way of asking, because truly what it looks like is not as important as what it's made of. This is just one of an example of what a house on Mars can look like. But we're looking at all of you to come and help us figure out, the phase 1 of this challenge has already passed, and it was the dreaming part. Is when everybody came and gave us these wonderful ideas of what a house might look like. Now we need to find out what kind of materials we can use to 3D print a house, and that's what we're here for. And hopefully in a year, we'll be back to with a webinar like this to ask you to help us actually make it a reality. So there's going to be more information about this. I just wanted to let you know that phase 1 has passed. Phase 2 is what we're talking about now, and hopefully in a year, we'll be talking about phase 3. Just a shameless plug here to let you know that Centennial Challenges have more than one challenge open at this moment. There's 4 challenges right now, so please come and join us in any of these also. The website is www.nasa.gov, and look for challenges, and you can have more information about the other challenges. We want you to come and join us, and with that, I would like to open it for a video for you to look at a little bit of a summary of what we want. And thank you so very much for being part of this, and we are all very excited. And again, on behalf of our group here, look forward to talking to all of you when we get together in August. So video, please. With us, and also want to give big shout out and thanks to our Bradley University and our sponsors, Caterpillar, Bechtel, and Brick and Mortar. So we want you. That's it.
All right, Monse, thank you very much. Let me introduce you to the rest of our experts joining us today. Next up is Lex Akers. He is Dean of the Caterpillar College of Engineering and Technology at Bradley University. Lex?
Good afternoon. Bradley University is a comprehensive private university located in Peoria, Illinois, the Midwest. We're excited about hosting the competition. Quite frankly, we view this as an opportunity to gather very smart, innovative, entrepreneurial individuals, teams, companies who really want to try to change the world. We think and we hope that this competition will help spur the development of disruptive and transformational technology. We can change, and I like to say worlds, not just Mars on how we would have our astronauts live, but also how we build habitats on our planet. We think, and in many ways, this is like when the early days of the PC computer was being developed by hobbyists and groups of people who got together and didn't know what they couldn't do, so they changed the world with companies like Apple and Microsoft. So we're excited about hosting this. We're going to have our students involved, observing, and they'll learn a lot from watching very innovative people come in and do fascinating things. We're excited about having you being part of this.
All right, Lex, thank you very much. Now I'd like to introduce Eric Reiners from Caterpillar.
Thank you, Mike. We're really excited about being part of this competition and event here at Caterpillar. Our role and our view, why we're participating here, it really starts with the customer and our ability to, through this competition, to drive innovation that can provide value to our customers in the construction industry. And we've done that historically in the past with NASA and other programs of collaboration on what we call mutual use technologies, or technologies that NASA needs to complete their mission of space exploration, but our customers would find value on here on Earth. And this is another example of that, but kind of in a different approach versus us doing the work ourselves with NASA internally, working with them to incentivize a much larger group of people to go after the problem, and address the problem, and drive a large amount of innovation. And to do that also with some other innovation leaders in academia, with our hometown university here with Bradley, as well as important customer Bechtel Corporation, and a leader of driving innovation in construction with Brick and Mortar Ventures. And so we're very excited about participating in this, and looking forward to seeing all of the creativity and innovation that the participants are going to come up with trying to solve this very difficult problem.
All right, Eric, thanks. Now I'd like to welcome Pete Corrado from Bechtel.
So hi, maybe you could swap the slide for me, Mike.
You bet.
I'm Pete Corrado. I'm a civil structural engineer, 40 years with the Bechtel Corporation. And as you can see from this slide, we have a long history of completing complex projects just about any place on Earth. So we're pretty excited about this opportunity to partner with NASA and the other sponsors in this challenge that's really going to exercise evolving means and methods of construction that are coupled with advanced material science. This is truly a once-in-a-lifetime opportunity to apply the principles of disruptive innovation. I think Dean Akers brought that up. And we're trying to disrupt a very traditional craft-based construction industry. This is a chance to shake things up that doesn't come along every day. We feel the results of this challenge are not only going to be one of the building blocks to extraterrestrial construction, but will also be a major agent for change right here on our home planet.
All right, Pete, thank you very much. And now we'd like to bring in Curtis Rogers from Brick and Mortar Ventures. Curtis.
Thank you, Mike. Yep, so I'm Curtis Rogers, Vice President at Brick and Mortar Ventures, and we are a venture capital firm focused on the design, construction, and maintenance industries. For the NASA team, we bring the perspective of the construction technology startup community to the team, so we sort of represent that community. And we're very excited about participating because we believe solution scarcity is contributing to the lack of construction productivity here on Earth. And we're looking to support the commercialization of advanced technology to improve the way we do things here on Earth.
All right, Curtis, thank you very much. Now, we know those of you joining us are anxious to get some of the details about how the competition is going to work. Before we do that, we'd like to bring in Tracy Prater from NASA to give us a little bit of background on the science that is the basis for this competition. Tracy?
Sure, thank you. If you could go on to the next slide for me.
Okay.
I'm Tracy Prater. I'm a materials engineer in the Materials and Processes Laboratory here at NASA Marshall, where I primarily support our additive manufacturing activities. So I'll give an overview of additive manufacturing and talk a little about how NASA is using that both in space and in how we develop hardware for space. So additive manufacturing is a term that's synonymous with 3D printing. It's simply the process of building up a material layer by first slicing a three-dimensional part file. So a machine then uses that sliced part file to generate tool paths that dispense material and deposit each layer in a precise prescribed manner. Additive manufacturing encompasses a very broad swath of technologies. It's everything from the fused deposition modeling systems that extrude plastics, which you might be most familiar with, to the more exotic area of manufacturing of metals. And that's where high-powered lasers fuse each layer together and transform metal powder or metal wire into a consolidated part. So next slide, please. So NASA, for a while, has heavily been engaged at the forefront of additive manufacturing technologies and is interested in leveraging the unique capabilities of the processes for our missions. So on what we call the for-space side, we're using additive manufacturing to reduce costs and lead time of highly complex propulsion components. And that enables us to accelerate development and testing of a new generation of rocket engines. Our in-space efforts are focused on reducing logistics, the amount of material that you have to take with you on a space mission, and enhancing crew safety by enabling a rapid adaptive response manufacturing capability. So our current capabilities on the for-space side include 2 printers on the International Space Station and an integrated feedstock printer and recycler that will be operational in 2018. So with in-space manufacturing, we're ultimately working toward deployment of an in-space multi-material fabrication laboratory that can provide on-demand manufacturing and recycling for plastics, metals, and even electronics. So I'm excited to see the expansion of 3D printing technologies into other sectors where this technology could be a benefit, and the challenge here, working with the construction industry, is a great opportunity for that. It's an area where 3D printing has the potential to increase productivity, impart design flexibility, and improve safety by enabling remote equipment operation. So when you think about the implications of 3D printing in construction, particularly to improve resiliency and durability of infrastructure, enable disaster response. It's pretty exciting stuff, and this challenge is a great example of how NASA's efforts in technology development for space can also be incredibly impactful here to us on Earth. So I'm going to turn it over now to Dr. Rob Mueller, who's an aerospace engineer at NASA Kennedy Space Center, and he's going to talk about the materials for the competition that you have to choose from and the rationale behind material selection.
Okay, hello, my name is Rob Mueller. I'm a senior technologist at NASA Kennedy Space Center in Florida. And I'm a subject matter expert for in-situ resource utilization, which is another way of saying living off the land. If we're going to go into space, we can't launch everything, and we certainly won't launch concrete into space. That's an obvious thing. And so if we can't launch concrete into space, how can we build infrastructure in space at the destination? So if we're going to Mars, how are we going to build structures on Mars? Well, fortunately, in space, we have a lot of dirt. Dirt is what we call it here on Earth, but in space we call it a regolith. So it's a regolith or soil, and the soil is made up of crushed rock, and the crushed rock contains minerals. And so these minerals can form the basis of a very hard material, which we can use as aggregate for a concrete-like material in space in order to build structures. Now, there's many ways of doing this, and ideally we would bring nothing from Earth. So we would use just the materials that we find on Mars. However, usually on Earth, a concrete has an aggregate and a binder. So this competition is structured to be completely open to anything you want to do. As long as you have a good structural material with good materials properties, we are not constraining anything that you wish to do. However, it is structured that if you use materials that are more relevant to Mars, then you will get more points. Now, you could win it by having materials that are less relevant but have higher strength, or you could have maybe a lower strength material that is more relevant to Mars. There's many, many ways of winning this. On Mars, we have mainly basalt-like materials, and so that's what we're focusing on. You'll get more points if you use basaltic materials. If you use sediments and evaporites like salt and gypsum, those are also found on Mars, but not in the same quantities as basalt. And then in decreasing importance, there's carbonates, granites, and metamorphic rock. And so if you choose to use aggregates made of those materials, then you'll have less points. On the binder side, you can use any binder you like. However, we do have an opportunity because on a mission, we bring polymers with us as packaging. And so we have up to 40% of a mass can be just packaging. Instead of throwing that away into a landfill on Mars, we certainly don't want to create landfills on Mars. We'd like to recycle it. We'd like to recycle it as much as possible, even 100% recycling. The material that's most relevant is polyethylene, LDPE polyethylene. And you can also see we've given you the recycle codes. If you look at some of these products made out of these polymers, you can see the recycle code on the bottom. And that will give you an indication of what material it is. So again, in decreasing order, you can see that polyethylene is the most available material on a space mission. Then we have the HDPE polyethylene, and so on down that list. Different polyethylene than nylon, polypropylene, aluminum foil, polystyrene, vinyl. Now again, you don't have to use these, but if you use them, then you get more points because they're available as recycled materials. Next chart, please. Okay, I think this is somebody else is going to talk to this.
Yeah, we were going to go into the basics of the competition. Do you have more you want to talk about, Rob?
There is a structure, a formula that we have. If you go into the rules for the competition, study that formula very closely because we have positive points and negative points. The positive points are to incentivize you to use materials that we have available on Mars. The negative points are designed to disincentivize you. In other words, we don't want you to use that, but we don't prohibit you from using it. For example, water. There is water on Mars. You can use water, but it's very precious. So we would prefer to use less water if possible, but it doesn't prohibit you from using water. But please study that formula closely, and that will be very important for your scoring.
Tell you what, Rob, we're going to go through some of the basics of the competition and give everybody an idea of the different levels and what's going to be expected. And then if it's all right, we're going to come back out to you a little bit later so you can go through the scoring particulars. But thanks for explaining the reason behind the 3D printed habitat challenge. So at this point, let's go through the basics of the competition. There are 3 levels to this competition. Each one progressively more difficult, but you're going to be able to test your materials and your processes along the way. And then we're going to offer some rewards along the way as well. So let's talk about level 1. As soon as we get it lined up on level 1 and not shoot through to level 3. With level 1, we're going to start very simply. You will print a truncated cone and cylinder, simple shapes, and this will get you started with building your 3D printer and developing your materials. Both of these will be tested to meet minimum criteria to qualify for level 2, and the 10 highest scores will be eligible for level 1 awards. So that's the story on level 1. Now we move on to level 2. And for that, you're going to print a beam. For level 2 testing, you'll be scored on both the material composition and the maximum load of the beam at failure. Now, this phase gets exciting because only the top 30 teams will qualify for level 3. And then once again, the 10 highest scores will be eligible for level 2 awards. Now, level 3, and that's really when things begin to get real. It's a head-to-head competition. The top 30 teams will be coming to the site you see on your screen, Caterpillar's Edwards Demonstration Center, to compete for the top award. Now, while level 3 should be a lot of fun, it's not going to be easy because you will have to print a cone, or a dome rather. And we've intended for this to be a difficult structure to print. You'll also print 3 compression specimens and 3 flexural specimens. So we're looking forward to seeing all those domes in person. The dome is clearly the wow factor of this competition. So you've learned enough about the competition to know that the structures you are printing are not only the culmination of a lot of work and innovative thinking in terms of materials. The materials that you print are really going to be the heart of the competition. So for that, we're going to hand it back over to Dr. Rob Mueller again to talk about how we're going to score those materials. So now I'll get you that slide.
Okay, this is what we call our sliding scale. And the idea behind this scale of materials is to open the competition up so that we have the most relevant solution for 3D printing a habitat structure on Mars, but it would still be relevant to construction on Earth because you could use other materials and win in different ways. So this is designed primarily to satisfy NASA's requirements, but it doesn't preclude you from using materials that are not as common in space. We think that there will be, in a concrete, we'll have a fine rock aggregate, a coarse rock aggregate, and maybe some trash recyclables as binders. And then we have this 3DP factor. That's the score you get. So in each category there, we would take a look at your aggregate and then see what type of material they are. For example, if it's crushed basalt igneous rock, then you would get a high score. Once you get the score from that sliding scale, you go to our formula, the rubric, and then we calculate your combined score. This table is an example of how we would do it. It's just an example. These numbers aren't accurate or designed to convey any kind of information. It's just an example. First thing you'll notice is at the bottom it says truncated cone score 0 or 100. So that's a binary thing. You have to pass that, and you get, if you pass it, you get 100 points. It's a pass-fail. If you pass it, you get 100. If you don't pass it, you get 0. So it's important to pass that. That's the first wicket you have to master. Then we have points for the indigenous materials and the imported materials, recyclable materials, and use of water. And you'll notice that the red points are negative. So we would prefer not to use imported materials on a mission to Mars, and we would prefer to minimize the use of water on a mission to Mars. However, we do have indigenous materials available, and we do have recyclable materials available on a Mars mission. So these are all different parameters and variables that you can adjust in any combination or any formulation you'd like to. And then, of course, there's no point in making a material unless it has some structural strength. And so we'd like you to do an ASTM C39 compression test, and then the strength will factor into the score. So ideally, you'd have a material that was commonly available on Mars that is very strong, that can be 3D printed. Now, I see on some of these questions that are being asked online, somebody's already asked, well, what's the percentage of binder that we're requiring to use? And we're not requiring you to use any percentage. That's completely up to you. However, if you did show up at the competition with a 3D printed dome made out of 100% polymers, it wouldn't be very strong and you'd lose. So we encourage you to come up with a very strong material, which is some kind of a concrete material made out of local rock aggregates with some kind of other technique which binds the aggregate together, and it could be even sintering where you have zero binder. So that's completely up to you. The competition is designed to focus on creativity and innovation, and we're looking to you to come up with some really interesting new solutions.
All right, Dr. Mueller, thank you very much for all of that. We think this is a chance to be part of something truly exciting and also truly forward-thinking. Your ideas, as you can tell, could be put to use by NASA to build a house on Mars. That alone is an incredible opportunity. But the other sponsors know that the materials and technologies you develop can have applications and help solve construction problems here on Earth today. So you have a variety of potential investors or collaborators or future employers who will be very interested in your ideas. So we hope that you're excited to form your teams and get started. Here are the key dates you need to know. Registration will close on January 31st, 2017. You'll submit your Level 1 results by March 31st of next year. The Level 2 deadline is May 31st of 2017, and then the Level 3 competition will be, again, at the Edwards Demonstration Center, and that will be on August 24th through the 27th of 2017. So this has obviously been a pretty quick overview, but still pretty thorough of really a pretty complicated set of tasks. You'll find very specific rules and more details on our website. So there you have them right there. You can go to www.nasa.gov/3DPHAB, and then to register and for all the official rules and documents, visit bradley.edu/challenge. So we will keep that up so that you can take a look at it. We'd like to open it to questions now. As you can tell, we have experts online right now. You can submit those questions through the chat feature. Some of you are already taking advantage of that. And then if you think of other things later, you can submit questions on the website as the competition goes on. So we'll let you get answers to those questions. Let's go ahead and deal with a couple other questions that have already come in dealing with some of the rules. And we're going to let Palin address those. First question is, all team members working on the challenge must be physically located in the United States. So how will this rule be applied to international participants?
International teams are exempt from the requirements of this 4.1.2 rule since they are not eligible for prizes. However, they need to be physically attend the Level 3 competition, but they can participate in Level 1 and Level 2 remotely. And ASTM standards and specimen submission requirements remain the same for Level 1 and 2. However, for the customs and visa requirements, they are done under the responsibility of teams.
Palin, if there are more than 4 international teams who would like to participate in the challenge, would there be a competition to select 4 international teams? And how are you going to choose the teams?
There is no limit to the number of international teams that can participate in Level 1 and 2. The 4-team limit applies to only Level 3, and only teams can meet the minimum success criteria for Level 1 and 2 will be ranked from highest to lowest, then the highest 4 international scores will be retained, and the remaining international scores will be removed from the list. Again, the list will be resorted from highest to lowest, and the top 30 teams will be eligible for the Level 3.
And again, this is all meant to be an overview. We invite you to visit those websites where you can get a lot more specifics and spend some time with the rules and regulations. Palin, another question is, what does participation in the challenge mean for international teams? Does it mean they can compete and be graded but cannot win the NASA prizes?
Participation in terms of physical printing, testing, and scoring should be nearly the same for all teams. The major differences are the international teams are not eligible for prize money, and the 4 international team limit that can advance to level 3.
There's also a question about time. How long will you give to make the dome structure during the Phase 2 Level 3 competition?
The allotted time for printing will be approximately 4 hours, and additional time for setup and cleanup will be also given. Likewise, additional time for curing and testing.
And finally, this question, can we use our own feedstock for making the structural member for Level 1 and Level 2?
Teams are required to procure their own feedstock for all levels of the competition. Pricing and grading of the feedstock prior to competition is permissible, and during the level 3 samples of feedstock may be requested by judges for further analysis. Likewise, specimens submitted for the level 1 and 2 are subject to competition testing as well.
Okay, and really, in addition to that, what kind of form the feedstock materials of recyclables will be provided at Level 3?
So they're going to procure their own feedstock for all 3 levels. So they will procure it. They need to bring it by themselves.
All right, those are all the questions that we have had coming in. I know all of you are able to see some of the questions coming in on chat, which are being answered by some of you. Would any of the rest of you experts like to also chime in on some of these questions?
Yeah, this is Rob Mueller, and I see there's some questions online about using regular simulants that are available today, like JSC-1A or Mars Mojave 1. So in the space industry, we do have certain regular simulants that have been made for space missions and for scientific study, and those are commercially available. In the case of JSC-1A, they make it, it's called JSC-2A now, and that's commercially available, and the Mars Mojave is not commercially available. So it's not easy to get hold of these simulants, but it would score very well if you did use a regular simulant, because it's very close to what you would find on Mars. So any kind of crushed basalt, I think, is close to a simulant that we would use typically at NASA. So my advice to the teams is to focus on the mineralogy and not so much on the pedigree, because we'll judge it on the physical and mineralogical characteristics. So if you have a crushed rock aggregate that's basaltic, that would score very high because it's close to what we have in these regions of Mars that are volcanic, and that's one of the ways of getting a high score.
Anybody else like to add to that?
Well, one other thing that's pretty obvious to everybody who knows 3D printing is this question of support structures. And the Rules Committee did discuss that at length. And Tony Kim has already posted an answer that I guess maybe we should read out his answer, but the gist of it is that supports are allowed, but they have to be automated. And so once you start printing, nobody's allowed to interfere. There's no manual intervention. It's a fully automated process. You are allowed to use supports, but you have to remove the supports before the end of the print. And so you cannot remove those supports manually. That must be done in an automated fashion. So it's up to you. You can build supports, but you have to remove them. It all has to be done automatically, no human intervention.
All right. Anybody else have anything to add to what Dr. Mueller just said? Again, let me repeat that we are throwing a lot at you right now, and it's probably difficult to remember some of the specifics. So we invite you to take a closer look at those websites that you see on your screen right now, the nasa.gov and the Bradley.edu challenge. So I think we're getting some other questions as we speak. Tracy, what kind of questions have you been answering?
So I've answered, let's see, there was the question about support structures that Rob already addressed, and we're also being asked about tolerances and how we assess tolerances. So structured light scanning or some sort of laser light scanning will be used to assess dimensional variation of the specimens.
We just got a couple other questions that all of you might be able to weigh in on. One of them is, can virgin polymers be used as feedstock, or do we need to source recycled polymers?
I can take that one. This is Rob Mueller. So we're really looking at the chemistry. So if you get the virgin polymer, I think that's fine, as long as it's truly the chemistry that you claim it is. And so if you have some documentation that shows the source of that polymer, so you can verify what it is, if it's a recycled polymer, that's fine, or if it's virgin polymer, that's fine too. But you have to produce some kind of documentation that shows what it is.
Another question that's come in is, in what form can the recycled materials be? Fibers, films, pellets?
It can be any form. We're not trying to constrain you at all. You can do anything you like to make a strong structural material. Bear in mind that it has to be made in space, so that's the challenge.
The next question that's come in, could support materials be incorporated to the printer structure?
This is Pete. I would say as long as the final printed structure is within dimensional tolerances, and you can figure out how to incorporate your support structure within those tolerances, then they'd certainly be allowed.
All right. Tracy, anything more on that?
Yeah, to my knowledge, there's nothing in the rules that would restrict you from, incorporating support materials directly into your printing device. However, as we've emphasized, if you do have support structures in the printed specimen, those have to be removed prior to testing, and they have to be done so in an automated fashion.
All right. I think we have another question that's just coming in here. And again, we direct you to those websites, not just today, but until the competition gets going. And it'll also give you those deadlines. While we're waiting for that question, let me go over those one more time with the deadlines. And again, the ones that you need to know, registration is going to close on January 31st of next year. Your level 1 results must be in by March 31st of 2017. Level 2 is May 31st, and then the level 3 competition will be August 24th through the 27th. Well, the question that's come in now is, will the final dome be tested in place, or will it be picked up and moved somewhere? For example, if it is printed upside down, will it be turned over for measurement?
Yeah, it's gonna have to be removed from that testing, from the curing place to testing place.
But I don't think you can print a dome upside down. We wouldn't do that on Mars, and it doesn't scale well. So you have to bear in mind that we're looking for technologies that could be scalable. So whatever you print, it will be printed in place and tested in place. and we'll have a test fixture. And maybe Pete, you want to talk about the test fixture?
Well, Bechtel and Caterpillar are still working on the most safe and efficient way to break these things in front of a crowd. So we haven't finalized that yet. Certainly there'll be a load applied to the upper ring. There may be a need to move the structures to a centralized testing location, but there'll be no rotation of the objects. It'll be a pick up and move, so there'll be no uprighting, rotating, or otherwise manipulating the final structure. So yes, it has to be printed in the orientation at which it's going to be tested.
All right. Everybody can hold tight for just a second. I think we're getting another question coming in. Let me go over those deadlines one more time, because it's probably going to be fairly key to what you do. The registration closes on January 31st, which is coming up. Your level 1 results by March 31st, and then a level 2 deadline on May 31st. The other question that's come in, is there any benefit to reducing weight in the specimens, i.e. printing a sparse fill structure versus a solid structure? Is strength to weight ratio important as well?
Your infill percentage will certainly impact your material strength, but the strength to weight ratio itself is not a direct metric in the screen.
Well, another important consideration is energy and time. So if you can build a structure with less material for less energy in a smaller amount of time, then that would be preferable. In space, we're resource constrained, and so anything we can do to be more efficient is of benefit. So I think strength to weight is important. However, it's not as important as if you were transporting it from Earth to Mars. We can probably live with a lower strength to weight, because we have these materials locally that we don't have to transport. So I think it's important, but it's not as important as it would be if you were transporting it from Earth.
Yeah, strength to weight is really a key driver for infrastructure that you're launching from Earth. Space is weightlifting, so to speak.
All right. Anybody else on that question? The next question we have, if the support structure falls off when the dome is picked up and moved for measurement, would that be acceptable?
No.
That's simple, right?
I think that's gaming the system, because in space we wouldn't move the structure. The structure would stay in place, and just if we have to move it to test it, then that's not representative of what we would do in space. So I don't think that's acceptable.
All right, I think we have another question coming in.
While that question's coming in, I'd like to go back to the strength to weight ratio. It's probably embedded in the scoring. If you're going to try and reduce the weight by some kind of sparse fill, you'll be reducing the mass probably of your coarse aggregate and increasing the mass of your binder. So if you have a nice recyclable binder, your overall score will go up, because I think the recyclable binder scores have higher value than the coarse aggregate would be. So again, Dr. Mueller said you got to look at those equations pretty carefully as you plan this out.
Yeah, I think that's really key, is understanding the rules clearly, and then formulating your strategy for the competition based on that and based on your skill sets that you think you can apply, and et cetera, to be competitive.
Let me give you another question that's come in. Are there any restrictions on publishing any potential findings if we develop a nice new binder and would like to publish in a journal? Are we restricted at all by this competition?
Well, I think, Monty, you need to answer that because that's an intellectual property question, and that's totally up to you. If you want to protect your intellectual property, then you have to choose how to publish that. But so I would say that you have to decide that for yourself. From a NASA point of view, I don't think there are any restrictions.
Now, the intellectual property belongs to the teams, so if you want to publish it, you're free to do that. So also want to make sure everybody knows that the questions and answers here should be captured to be put in the frequently asked questions in the website. So if you want to come back and, read the answers or have more questions after this webinar, you should be able to either find them there or ask them so we can answer and post them there.
We also should remind everybody this webinar is also being recorded. Where can people take another look at this webinar?
I am assuming that the website will have the link to it after.
The NASA website or the Bradley website?
No, they'll be published on YouTube, and there'll be a link on the Bradley website.
Right. It will be in the Bradley website. And if you go to the NASA website, it will send you to the Bradley website. So either, if you only remember the NASA one, it will link you to that.
Okay. And Palin has put that link up right there. Anybody else out there with any questions? We have just a few more minutes with all of our experts on board here. And if
also,
everyone can...
I want to encourage the teams that are listening right now to, if you're interested in possibly, interacting with the other teams, we probably we'll try to have an activity where you guys can talk to each other, or a web page or something. So, there might be, you might want to advertise a position in your team that in an area that you do not have, and we can try to help you with that, hopefully. So we can do that in the website, or we have done that with other challenges. So in case you're missing an expertise in an area for the challenge, please reach out to us. We will be welcome. We will be happy to help you.
All right, at this time, I don't see, no, I think we are going to get a couple other questions. So if all of you can kind of hold tight. This question is, I just want to verify, the time allotted for printing the dome was stated as 4 hours. I calculate the volume as 115,208 cubic centimeters. This equates to a printing rate of 28,802 cc per hour. It seems high.
So that equation was based on about say if you have a 1-inch diameter outlet traveling at 25 millimeters per second was how that was calculated for the dome.
Mm-hmm.
That seems consistent with what we've seen in 3D printing.
Yep, and Pete, with Bechtel, has there been any changes to the schedule?
I haven't seen any changes to the schedule yet, so.
Yeah, that's accurate. 4 hours.
Well, seeing that it doesn't appear we have any more questions, would anybody like to make any closing comments on this and anything that we have not dealt with in the last 45, 50 minutes, but should?
From the NASA side, thank you, everybody. Please let people know about these. The more competitors we have, the more we potentially disrupt the current technology and make incredible advances. So, you know, if you are not interested in participating, but if you know of other people, please do pass the information along. And again, all of us are here to help, so please reach out to any of us, and we'll be happy to connect you with the right person and to answer your questions and to provide you any information that you might need.
And from Bradley University, please go to our website. We have frequently asked questions on there. You can also communicate with us through the website.
And as we've been saying, that really is the best place to go back to review what we've been talking about, and to see any other information that you might want to know is to go to the bradley.edu/challenge site or the nasa.gov site, both of those links that you see on your screen right now.
And this is Eric Reiners from Caterpillar, and I'd just like to comment that for the teams that are considering this, I think it's a tremendous opportunity for not only innovation and creativity, but also through that ability to really affect humanity. So as we look at throughout this century, the projected population growth worldwide and the shift in standard of living, there's going to be significant demand for housing worldwide, and housing in areas of the world where you know, people are dealing with less than desirable situations today, and this technology really affords a way to provide that housing cost effectively, or offers that potential and the real ability to impact humanity here on Earth. But then, of course, from the NASA perspective, actually enabling humanity's presence on and the ability to live on other planets as well. So I think it's very exciting from that standpoint, and really encourage everybody that's contemplating this to think seriously about taking on this challenge.
Yeah, it really does seem to be nothing less than a chance to be part of history. So it's an exciting opportunity. We hope that that you're just as excited about those opportunities ahead. We wish you the best of luck, and again, refer you to those sites to get any information along the way. Our thanks to everybody who participated today, and hope you have a good day.